So hello, welcome to this tutorial on mutable borrows. This picks up where the ownership and shared borrows tutorials left off. So when we last met our two friendly stick figures, they had just learned to share with one another. And in particular, we were able to give a reference to a book so that many people could read it at the same time. But there's one other kind of sharing that we sometimes like to do in programming, which is we'd like to be able to delegate not only the ability to read a data structure, but to mutate it, right? So that's kind of like if I have a book and I tell my friend, here you go, Principles of Compiler Design, great text. And then they take it and they go ahead and make some changes to it, right? And they end up, say, rewriting some of the paragraphs, making a few edits, and then giving it back to me and saying, here you go, enjoy this new updated copy. And I say, thank you, much improved. Right, so that's kind of what we're going to do now by using data structures. So here's a snippet of code, very similar to the one we've been working with. Only this time, the helper routine that we call, which is called update, is not only going to read from a string that we own, it's going to write to the string that we own. And so it begins by saying let mute name equals, I left out here, but format bang, let's say, and that will allocate the string buffer that we have. And then when we call update, you see that the argument is no longer ampersand string, but ampersand mute string. So the way to read that is it's a mutable reference to a string, right? And on the other side, when we lend it out, we don't write ampersand name, we write ampersand mute name, so that we can lend out a mutable reference to our name. So in terms of what happens at runtime, we end up with the update function having a mutable reference. Right? Now this is actually the same at runtime, but logically, mutable references behave somewhat differently. So you may not have noticed that, but I just faded the book a little bit. That's because when we had a shared borrow and a shared reference, we could give away as many copies of that shared reference as we want. We're going to see that mutable references, you can only have one copy of them at a time, and while there's a mutable reference that's active, you lose access to the original variable. So while we have this mutable reference to name, we can't use name anymore. So that's why I faded the book slightly to indicate that it's only accessible now through this mutable reference. But anyway, update doesn't care about that. Update has a mutable reference, and it can go ahead and use it. And the interesting thing is, when it makes mutations through this reference, it's actually changing the string that the function main owns, right? So here, when it calls name.pushStir, it's actually going to mutate name in place. So that means that the variable name is going to change from having the old string to the new string, which has some new text appended on the end. And that means that when we return, well, this mutable borrow is going to end. Again, update didn't own the data, so no data gets freed. It was just borrowing the data. And we come back, and now we now have full access to our string buffer again. That's because update finished with that mutable reference. It's no longer in use, so we can use it again. And it has new contents. Right? So when we print it, we're going to see something different than we saw the first time. And of course, we're still the owner. So when main returns, that means that this data is going to get freed. So in this and the last two tutorials, we've now seen the three primary ways to interact with data in Rust. Right? The first thing we saw was ownership. If you own some data, that means you control all access to it, and when you're finished with it, that data is going to get freed. The next thing we saw was shared references. If you have a shared reference, you can have a lot of different copies of that shared reference, all reading from the data and all active at the same time, but there's no way to mutate the data while it's being shared, or at least you have to go through special APIs we haven't seen yet. And the last way that we just saw is a mutable reference. In this case, the only way to access the data is through that mutable reference, right? We lose access to the original variable temporarily. And so we know that that mutable reference has exclusive access. Nobody else can read from that data, and no one else can write to that data unless they go through this reference. Okay, so we're back to these awesome dogs again. I'm going to jump back to play, and I'm going to try to give you a feeling for these mutable reference rules, how they relate to actual code. So here we have our example. This is actually the ownership example we saw before, where we give ownership twice and get an error. I'm going to modify this function so that it takes a mutable reference to a string. Right? So we can write ampersand mute on both places. we have to declare the string itself to be mutable. And then we can actually push some data onto the string, right? And let's move this print up here so that it comes after and we can see the effects. So when we run this, now we started with fellow rustaceans, and we see that we're going to get, we've written 2 copies of the word foo on the end. Okay. Now what I want to do is I'm going to make a variable that has this mutable reference, just like we did before with the sharing. Right? And now let's try to run this code now. Well, we actually get this error, cannot borrow name as immutable, and it's pointing to this use of the word name. So this is illustrating exactly this property I was referring to, that mutable references, while they're in scope, kind of get a exclusive access to the variable that's underneath them. Right? So here we created the variable r, which is a mutable reference, and for the remainder of its scope, that means we lose access to this variable name. So we can change this by introducing a subscope. And now the scope of r is just going to be this portion, right? And it stops at this closing brace, and now we have access to name again. Very good. And one last thing I want to show you is, suppose I tried to make a second reference while the first one was active. Well, naturally, that's not allowed. So here I'm getting an error right here where I tried to make a second mutable reference to the same variable name, but in that case, the first reference, r, would no longer be exclusive, right? We could use r or r2, and we want to guarantee that you only have one mutable reference at a time. And the last thing I'm going to say is, at the first version of this code, and the version you would write most often, created a reference and passed it in as a parameter. So that's effectively a kind of shorthand for making this explicit variable that has a very narrow scope, right, tied just to this function call. So that's why we can kind of repeat this as many times as we like, and we never get an error about having more than one mutable reference, because really at any one time, we only have one mutable reference. All right, let's go back to the slides. So we've seen now what the Rust rules are, and we kind of have a feeling for how a mutable reference works and how it gets exclusive access to the thing being mutated, but we haven't really seen why. And so to explain that, I want to dive a little bit into the question of safety. And by safety, what I mean is this is basically the key rules that allow Rust to avoid using a garbage collector while also avoiding segmentation faults, right? And to allow Rust to have threads while avoiding data races. It's basically all based on these ownership and borrowing rules we've been talking about. So here's the example I want to go through. It begins, like many of our examples, by allocating a string, right? And then if you look, it creates a reference into that string called slice and pushes a new letter onto the string. So before the string had rustation, now it's going to have rustations with an S at the end. And then it prints that slice. And you might expect this, for example, to print ustations with an S on the end. But what actually happens if this code were to run? Well, let's execute it. We're going to kind of see how the machine model works. So the first thing that would happen is we'd create a string. And a string, as I told you, is represented by 3 fields. A data, which is a pointer to a buffer. So some area in memory that has the word rustation in it. And then a length and a capacity. And this buffer has a size, right? And it has to be at least as big as the string. And usually there's some extra space. But let's say that this time, for whatever reason, the buffer has size 9, which is the length of the word rustation. So both the length and the capacity are 9, which means the buffer is completely full. Okay? And now we're going to come along and make a slice into that buffer. Now a slice at runtime is represented by a reference directly into the data buffer of the string. So we don't really even know where the original string was. All we have is the data at our fingertips, right? And we also have a length. In this case, the length will be 8 because it's the rustation minus the R. And now we want to push an S at the end. And this is where things get interesting. Remember I told you our buffer was full, so it only had space for 9 letters? Well, now we need 10. What we do is we allocate a new buffer, Usually you make it twice as big, though you don't have to. Let's say we do. So this buffer will be 18 characters big. And then you copy over all the old data. So now it says restation. And then you put your new data in. Now it says restations. So we'll have a length of 10 and a capacity of 18. But now we have two buffers. We don't really need the old one that had the old data, so we're going to free it. And then we're done with the push stir operation. But here we come to print the slice. And now we get into problems. Because this slice is still referring to the old memory, right? When the buffer was copied, the slice can't get updated. Remember, there's really no link between the slice and the string itself. And that's what we call a dangling reference. Reading from freed memory is undefined behavior, so technically this program could do anything. What it usually will do is, usually it'll print a station, at least whenever you're testing it, but once you get to your customer's computer, it'll start printing secret keys from their memory or who knows what, right? So that's not a good situation to be in. And we would really like this code not to execute. And in fact, in Rust, it doesn't. It gets a compilation error. So basically, the way Rust's solution works, as we've seen, is it's a kind of compile time read-write lock. Now, a read-write lock is this handy thing you can use in parallel programming, where you say, I have some data, and I want to allow either a whole lot of readers or exactly one writer with no readers, right? No other threads reading at the same time. And this is how you can avoid data races. It's also exactly the model that Rust enforces at compilation time. And of course, there's no real lock here, right? It's just a metaphor to help you kind of process how it works. So if we look at our example, the basic rule is when you borrow something, either as a shared borrow or a mutable borrow, you can't mutate it through the original path while it's borrowed, right? So here, when we make this slice, we're going to borrow the variable buffer, actually a subset of the buffer, but it's not an important distinction here. And we're going to say, let's figure out how long, this is called the borrow's lifetime, how long is that reference in scope for / going to be used, right? So here we see that the reference is created by the ampersand expression. It gets stored in this slice variable. The slice variable is in scope until that closing brace. So that means this is the lifetime of our borrow. So you'll often hear this word lifetime used in Rust tutorials and so forth. A lifetime is really a span of code in which a reference is used, right? So here, the lifetime is starting from the let and going to the closing brace. And we usually give lifetimes names. I'm just going to give this one the name tick L. That's Rust notation. It's that tick L that's on the right side of the screen. A lifetime is a name that begins with a tick. Right? So here we'll just call it tick L just for having a name to use. And then we look and we say, during this lifetime tick L, the original variable buffer is locked. Right? So it's got a read lock, essentially. That means no one can write to it. So that's exactly why when we see this call to buffer.pushStir, which occurs in the middle of that lifetime, we can call it an error. The cool thing about this is that this lock only lasts as long as the reference is in use. So here we have a variation on the example. And what I'm doing is I've moved that code we had before into a loop. Right? So here's the borrow, the same kind we saw before, that's going to borrow the variable buffer, and that means we're going to have a lock until the variable slice goes out of scope, right? But here, the variable goes out of scope at the end of the loop. So that means this region of code, in this region of code, buffer is read locked. So that means we get an error here in the loop if we try to call buffer.pushStir, because that falls within that region of code. But after the loop, that's perfectly fine. The buffer's not borrowed here, right? So mutability in Rust, as we've seen a number of times, is really a property that isn't fixed. It depends on where in the code you are, right? The same data becomes immutable during the loop while it's borrowed, and then becomes mutable later after the loop's over. Okay, so that's it. It's time for the exercise. As usual, I want you to go down and click below on the exercise link. Or if you're not in the Into Rust website, go ahead and grab that URL from the lower left corner and do the same thing. And then I'm going to take you over to the play site now. I'll walk you through the example. You can give it a try and then come back and see the solution. Okay, so here's the code. for the exercise. I'm going to walk through it, and then we'll look at the challenge that you have to solve. So the first thing it does is it calls this toWords function, which we've seen before. toWords returns a pair of strings. The first one is going to be fellow, the second one rustaceans, and these get packaged up into a pair and returned, right? So basically it makes two buffers and gives ownership of both of them back to its caller. The caller is going to store those buffers into two separate variables. The first one is called stir1, and the second one is called stir2, and then it calls join words. You see that join words is a function which takes two string arguments, and it takes ownership of those strings. And what it does is the prefix, that's the first string argument, it's going to modify and append the second string argument onto it. Right, so first it puts a space, and then it goes through each character in the suffix, the second argument, and pushes that character onto the string. And then finally it returns ownership of this string back to the caller. Right, so ownership will flow for the prefix. Ownership will flow kind of from here, from fellow, up to stir1, into the join words function, where we have ownership here, and then we return it here, and that actually gets assigned back into stir1. Right. Now I want to stop for 1 second and talk about the mute keywords here, because they're kind of interesting. First of all, you see that, let's go back to the main function, you see that this variable stir1, which is inside this tuple, can be declared as mute. Really, you can put the keyword mute next to any variable binding, wherever it appears. So here we're saying the variable stir1 is mutable, and the reason we're saying that is that we're going to assign to it, we're going to move out from it here, and then reassign it here. Right? So because we're reassigning it, we have to declare it as mute, since that introduces the possibility that if we read from it twice in the function, we are actually going to see different values, right? Because this new assignment is going to have the concatenation of both strings. And the second interesting thing is this argument is declared as mute. And when you declare an argument as mute, what's sort of interesting about that is it looks like it's parts of the function signature, but actually it's really kind of a private detail of join words. The caller doesn't care, because the caller has given ownership of this string to you, so they can't access it anymore, right? So if you mutate it, it's really none of their business. So when you see mute before the local variable, that means join words, before the argument name, that means join words is saying, sort of to itself, I'm going to mutate this prefix, right? Okay, that's what this code is doing. And if we run it, we expect to see fellow space rustaceans. Let's do that. Yay, fellow space rustaceans. Great. So what is the challenge? The challenge is to convert join words to use borrowing instead of ownership, right? So the idea is that we are going to, in here, join words now takes ownership of two strings and gives back a third, or ownership of a string. What we wanted to do is to mutate these strings in place and have no return type at all, right? So these two arguments should be some kind of references. So there should be no ownership transfer happening. All right, I'm going to leave it to you guys to go ahead and give that a try. One thing I want to point out, a lot of people find it a little bit tricky to get everything right, so you might like to take a look at this hint if you get stuck. Just open that URL. Okay, go for it. Okay, good. Let's go take a look. All right, so we said what we want to do is mutate the strings in place instead of giving ownership away, and then we want to stop giving ownership back. So I'm going to do this in pieces. The first thing I'm going to do is say, okay, this second argument, there's really no reason for us to take ownership here. We actually want to borrow this string, and we're only going to read from this string, so a shared borrow suffices. So I can put an ampersand here, and then I'm going to need a corresponding ampersand here, right? So if we compile, we'll see I took a shared borrow, I get a mismatch types error. This is basically saying this function expects to borrow suffix, but you gave it ownership. So let's put the borrow here. And now this code will just work. But we haven't really solved the full problem because we're still taking ownership of string 1, right? And so what we have to do is we have to put a mutable borrow here so that we can mutate string 1 in place. And now, because we're taking a mutable borrow, there's actually no reason for us to give ownership of the string back, right? Basically, we were doing that before because we were going to take ownership, make some changes, and give you back a modified version. But now we're just going to have a mutable reference directly into your local variable and mutate it right there, right? So that means we don't have to have a return type at all. And take away, I should say, if this was the return expression, I'm going to take that away. And now I'm going to go up here, and because I'm not returning anything, I can get rid of this local variable stir1, or I can get rid of that assignment, and instead do a mutable borrow. Right? So now I'm giving mutable access to stir1 to join words, which will mutate it in place, and now the code will run, and that's good. The only thing is, there's one last point. Here you see this keyword mute. We actually don't need this keyword here at all. And that's because we're not reassigning this reference, right? We're not changing this to be a reference to some other string. We're just mutating the data that the reference refers to. So that means the mute here suffices. So if we take that mute away and we run the code, it'll still work just fine. Okay, great. Okay, so that was the challenge. I'd just like to make a few other minor stylistic adjustments. The first one is, here you see I'm taking a reference to a capital string. That's usually not a very useful thing to do, because having a reference to an entire string buffer isn't usually particularly important, and it doesn't give you any abilities over having a reference to a subset of a string buffer, at least a shared reference. So we can change that to ampersand stir. And now the code is going to work fine, but there's one other thing we might want to do, which is if you're pushing an entire string, you can just use this helper function push stir instead of the for loop. And if we write this code, now it works great. Okay.